All right, so here's a photo of Robert Wilson and Arnold Penzias, who won the 1978 Nobel Prize in Physics for their discovery by accident of the cosmic microwave background radiation. And that's what persuaded cosmologists to abandon all hope in the steady state hypothesis. The steady state cosmology was one where in the homework you studied a universe dominated by a cosmological constant, and such a universe expands exponentially for all time. There would be no Big Bang, because if you think about it, if you have that the scale factor is given by an exponential with time, then the scale factor is never zero. If you run time backwards, it just gets smaller and smaller, but it never hits zero. So such a universe would be eternal. It would have been there forever. And the idea behind the steady state hypothesis was that the universe essentially looks the same at all times. Not literally the same, not that there's no change happening, but that no matter when you lived, you would see essentially the same kind of cosmos we see today, full of galaxies that are receding away from us and so forth. And in order to make that work, there would have to be continuous creation of matter. There would have to be a little bit of matter coming into existence in the empty spaces opening up between the galaxies. So of course, that would be problematic. But if you calculated the rate at which matter would need to be created, it was really quite small. I don't remember, but it's something like a hydrogen atom per cubic meter per year, or something like that. Some pretty small rate would do the trick. And that was considered a viable hypothesis in competition with the Big Bang theory until the cosmic background radiation was discovered, because in the steady state hypothesis, there's no reason for there to be a cosmic microwave background. In the Big Bang hypothesis, you would expect it to exist. So the cosmic microwave background is microwave radiation filling the entire universe that is a leftover from the Big Bang, from the hot early universe, redshifted into the microwave region of the spectrum. Now its wavelength is, the peak is at a wavelength of about a millimeter, but that would have corresponded to a temperature of about 3,000 Kelvin when what we call recombination occurred, when electrons combine with protons to make neutral hydrogen atoms for the first time, which means recombination is a terrible name, because it's the first time combination has ever occurred. So it should have been called combination instead of recombination, but we're stuck with it. We use the same thing we do for like H2 regions when ultraviolet light ionizes hydrogen atoms, and at the same time electrons combine with free protons to remake hydrogen atoms. That's recombination. In the universe, it was the first time neutral atoms had ever existed, so it's kind of silly to call it recombination when it's the first time that it ever occurred. So this is the Bell Labs horn antenna that they were using to communicate with the new Telstar satellite in New Jersey. They worked for Bell Labs, and they had this unexplained hiss in the output of the antenna, and they tried everything, including cleaning out pigeon dung in the antenna, trying to get rid of that hiss, but it was still there. It was coming from all around the sky, so it didn't seem to be some source within the Milky Way, which would rise and set with the stars. And then meanwhile, they got wind of a prediction that the universe should have a cosmic microwave background, and it was realized that that is in fact what they had accidentally discovered. So when it comes to Nobel Prizes or achievements like that in general, it helps to be good, and it helps to be lucky, and it helps to be lucky and good especially, and they were lucky and good. Their persistence paid off, and they just happened to see it, is what it comes down to. So the idea is that in the early universe, it was hot enough that everything was ionized. In the ionized early universe, light was trapped by free electrons, and radiation had a Planck spectrum. It was very nearly in thermodynamic equilibrium, and field is at a high enough temperature that you can't form free atoms. As soon as a free atom might have formed, a collision or an ionization would immediately destroy it. So the universe was a plasma filled with photons. And free electrons, as you know from when we studied stars, in stellar interiors, they scatter electrons. They're a source of opacity. And in the early universe, then, the free electrons made the universe essentially opaque. The photons couldn't travel very far. The mean free path wasn't very large. As a result, you can kind of think of there was a universal fog. So the analogy is that the early universe was foggy everywhere, so there were not trees and mountains, obviously, and so forth, but look, fog, okay? As the universe expands, the expansion of the universe is continuously stretching out the wavelengths of the photons, so the temperature is dropping. It always has a thermal plotting spectrum, but the expansion of the universe, by expanding the wavelengths, cools the universe down, and under the conditions of density in the early universe, unlike in stellar interiors where about 10,000 Kelvin is where hydrogen goes from ionized to neutral, it was more like 3,000 Kelvin in the early universe was the transition between ionized and neutral hydrogen. And so, at the age of recombination, we call it, when the universe had dropped to a temperature of about 3,000 Kelvin, the electrons were able to combine with protons to make neutral hydrogen for the first time, and we call that recombination. And the universe, all of a sudden, essentially became transparent. Because remember that neutral hydrogen only wants to only wants to absorb specific wavelengths. And so it became essentially transparent at most wavelengths. And so recombination was like the fog suddenly clearing. Okay? So that's our story so far. The universe became transparent when roughly 300,000 years after the Big Bang, when the temperature had dropped to 3,000 Kelvin, and hydrogen became neutral for the first time. Yes?
Could you say again why it was hazy? It's
because of the free electrons. So in other words, when it was a plasma, free electrons scatter photons of all wavelengths. And so it was hazy because of the free electrons in the plasma. But the fog lifts when recombination occurs, when the universe was almost 300,000 years old and the temperature had dropped to 3,000 Kelvin. Yes?
Is the reason why the temperature is different just because of the sheer number of like electrons?
The temperature was different?
For the 10,000 to 3,000.
Oh, it's the density, when you put it into the Saha equation under the density condition that happens at a lower temperature. Yeah. Any other questions? Okay, so what does this mean we see today? When we see the cosmic microwave background, of course we don't literally see it with our eyes, but when we detect the cosmic microwave background, or if we could see at microwave wavelengths so that we could literally see it, what we're seeing is what we call the surface of last scattering. So remember that when you look out into space, you're looking back in time, right? So if you see something that is 100 million light years away, you're seeing it as it was 100 million light years ago. Now when you start to get to billions of light years, it becomes trickier. In other words, something that, when you get something billions of light years away, the universe has been expanding significantly since that time. And so we run into the idea that the distance today isn't the same as what it was when it emitted the light. But the idea is, the further out in space we look, the farther back in time we see. So when we look out into space far enough that we're seeing the time of recombination, then beyond that, the universe is still opaque, and so the farthest we can see is to the time of recombination. Any earlier than that, for things that are far enough away from us that to see them we would be looking to the time when the universe was still opaque, we can't see it. So in other words, there's what we call the surface of last scattering, and that's where we are seeing the cosmic microwave background photons coming from. We are seeing photons which were last scattered by free electrons at the time the universe became transparent. And then after that, the photons were able to freely stream through the universe. And at present, the surface of last scattering is about 45 billion light years away from us, 14,000 megaparsecs. It's about 45 billion light years away from us. So when we see the cosmic microwave background, the current proper distance to it is about 45 billion light years. So I'll ask the question, in a universe that is only 13.8 billion years, how can we be seeing things that are 45 billion light years away? Because of the expansion of the universe, right? Because the expansion of the universe has carried that surface to a present distance from us of about 45 billion light years. Okay, so you can kind of think of the surface of last scattering as like a photosphere, if you will. We can't see past that into the earlier universe because the universe was opaque back then. Any questions? This can be a subtle concept to understand.
Simple question.
Yeah.
What does it mean redshift of 1,100?
So in other words, also when we look farther away, things are moving away from us faster due to the expansion of space. And so what we're saying is that Z for the surface of last scattering is about 1,100. So put it another way, given that the scale factor corresponding to a given Z is 1 over Z plus 1. Well, 1,100 plus 1 is 1,101, doesn't make much difference. So in other words, what we're saying is that the universe is now about 1,100 times larger than it was at recombination. And so the wavelengths are about 1,100 times longer now than they were at recombination. And if you go to Wien's law, which says that the peak wavelength is inversely proportional to the temperature, then at recombination the temperature was about 3,000 Kelvin. Because the wavelengths have been stretched by a factor of 1,100, that means that the temperature of the radiation from Wien's law has fallen by a factor of about 1,100. So the thermal spectrum corresponding to 3,000 Kelvin combination, it's been redshifted to be 3,000 over 1,100 is about 2.7 Kelvin today. So the cosmic microwave background radiation today is a thermal spectrum at about 2.7 Kelvin. It's much colder now than it was back then. So if you had somehow managed to be alive at the time of recombination, impossible. Nothing could have evolved before the universe stopped being a plasma. Everywhere around you, the sky would have been similar in appearance to the surface of a red giant star at around 3,000 Kelvin. The universe would have been like just a bright reddish, whitish, orange color everywhere. But now it's a microwave spectrum. So this is showing this idea that the expansion of the universe has shifted all the wavelengths. And one can show that if you redshift a Planck spectrum, it's still a Planck spectrum. So in other words, a blackbody spectrum that is redshifted is still a blackbody spectrum, just at a lower temperature. It works out nicely as far as that's concerned. The cosmic background radiation is perhaps the closest thing to a perfect black body that we know of. These are cosmic background explorer measurements from the late 80s, early 90s, the first satellite that was launched to look in detail at slight temperature variation in the cosmic microwave background. They're very slight. There's a Planck spectrum at 2.728 Kelvin. The orange-red dots are data from COBE, and as it says there, the uncertainties in the measurements are actually much less than the thickness of the line. It's an almost perfect thermal spectrum. It's remarkably close to a perfect black body spectrum. But it's not perfect. There are slight variations in different directions on the sky of the temperature of the radiation. I wish that this had been done in Kelvin instead of centigrade. But in any case, just as we can map the surface of the Earth on one of these ovals like this, that's a particular map projection, we can map the celestial sphere onto an oval in exactly the same way. The projection is generally done so that the plane of the Milky Way is along the center, and the researchers had to subtract off microwaves from the Milky Way in order to produce this map. You have to subtract off lots of sources of error and noise and so forth. And when you're done, this is from the WMAP, the Wilkinson Microwave Anisotropy Probe, what you see is very slight temperature variations from one part of the sky to another on the last scattering surface of the cosmic microwave background radiation. And so you can see that the temperature, the total range of variations is about 0004 Kelvin out of 2.7 Kelvin. So we're talking parts in about 100,000 or so. Very slight deviations from uniform temperature in different directions of the sky. And this has absolutely revolutionized cosmology because we can theoretically understand the origin of these slight variations, and by carefully analyzing the strengths of temperature variations of various angular sizes on the sky, we can deduce all kinds of interesting things about the universe, is what it comes down to. So what we are seeing, it turns out, are sound waves in the early universe. That's what these slight temperature variations represent. There were sound waves in the early universe, and what seeded those sound waves were quantum fluctuations before inflation that were stretched out to macroscopic size after inflation, that then allowed dark matters to start falling into those slight temperature, those slight density variations when the universe was radiation dominated, and then when it became matter dominated, ordinary matter, the kind of stuff we're made of, began falling into regions of higher density, but when it falls into it, its pressure rises, and so it will rebound back out again and oscillate, and so it sets up sound waves in the early universe, and we are able to theoretically calculate which wavelengths ought to be strongest in those sound waves, and learn all kinds of interesting things. So this is the stuff I'm going to have you read about in that book, about the details of what these sound waves tell us about the early universe. And what I want to start talking about now is inflation. This idea of cosmic inflation explaining some things that were puzzling about the cosmic microwave background and the universe in general before the inflationary hypothesis was produced. So, at this point, what questions do you have? This is strange stuff. It takes a while to intuit what's going on here. But it has told us, like I say, this has revolutionized cosmology, the ability to make these maps like this. Yes?
What did you mean when you said dark energy fell into?
No, dark matter. Careful, there's dark matter and there's dark energy.
Okay.
So there were slight slight variations in the curvature of space-time caused by these quantum fluctuations, because where there's more energy, space-time, more energy corresponds to more gravity, corresponds to curvature of the space-time. And so essentially these slight fluctuations in the structure of space-time from these quantum fluctuations that were submicroscopic before inflation, but got stretched to more macroscopic sizes after inflation. Dark matter doesn't interact with photons. And so the dark matter was able to, via gravity, start falling into regions that were a little bit enhanced in density because of these perturbations that got expanded by inflation. So the dark matter can start self-gravitating and collecting before baryonic matter can, because baryonic matter interacts with photons, and when the universe was radiation dominated, the photons kept scattering off of baryonic matter particles, and much too strongly for their gravity to allow them to start coalescing. But dark matter didn't have that problem, if you will, because dark matter doesn't see photons. So dark matter was able to start congealing before baryonic matter was. And then, after the universe became matter-dominated, when it expanded enough to allow the matter density to be bigger than the radiation density, that's when ordinary matter could start responding gravitationally to these density perturbations that the dark matter had already started falling into. Then the ordinary matter starts falling into it, but it will bounce back and oscillate and make sound waves. And those sound waves are what we're seeing here. When you have a bigger compression, it's hotter, and when you have a rarefaction, it's cooler. And so we see hotter and cooler regions because of these oscillating sound waves, and where there was higher density, we see slightly hotter regions, and lower density, we see slightly cooler regions. That's the basic idea. And that reading I give you will expand on that, but that's the basic idea. Okay, any other questions? All right, so let's inflate, as it were. So, cosmic inflation. Gotta repoint the camera here. Cosmic inflation, yes.
As opposed to monetary inflation.
Yeah, the politicians need to do something about this. They need to legislate away this.
We must stop cosmic inflation.
Yes.
That'd be a great April Fool's joke.
Yeah.
Like the president to give like a State of the Union address on April Fool's Day. Like,
Yeah.
we need to stop cosmic inflation.
That's
It's too big. Too much.
Yes,
Our economy cannot handle this kind of inflation.
that's right.
Mainly because it has nothing to do with it.
If we don't stop it,
No one will.
then what? Yeah, then something, I don't know. Actually, it stopped long ago. Well, no, it started again, but in a much more gentle way. Cosmic inflation. Three problems with the standard hot Big Bang scenario. Number one is called the flatness problem. Why is the universe at all close to being flat? Omega, the density parameter, is close to 1 and would have been much closer to 1 in the past. So much so that it begs for explanation. Two, I'll let you catch up for a moment. Two is the horizon problem. In the standard scenario, and by standard I mean no inflation. In the standard scenario, points on the last scattering surface more than 2 degrees apart would be outside one another's cosmic particle horizons. At the time of recombination. Meaning they had never been in causal contact. They had never talked to one another since the Big Bang. They had never been in causal contact. No energy or information was ever shared between them. So then the question is, why are they then at the same temperature? How can they be at the same temperature if they never shared any energy or information with each other? Nobody had a good explanation of that before inflation came along. And number 3 is the monopole problem. Remember from E and M, as far as we know, there are no magnetic monopoles. Particle physics grand unified theories predict that magnetic monopoles were produced in abundance when the strong force broke off from the electromagnetic force in the early universe. So-called GUTS, grand unified theories, which unify the strong, weak, and electromagnetic forces, try to describe them by a single mathematical description. Predict that something like 10 to the 82nd power per cubic meter of these things should have been around. When the strong nuclear force broke off, from the electroweak force, it's called spontaneous symmetry breaking. In the early universe. So current thinking is that right after the Big Bang, all four forces were unified, and then when the universe was like 10 to the minus 34th seconds old, that the strong nuclear force would, or gravity would separate first, and then the strong nuclear force would break off from the electroweak, unified electromagnetic and weak forces at an age of about 10 to the minus 34 seconds of the universe, creating, it turns out, and I don't know the details, but creating gazillions of magnetic monopoles, each with a mass of about 10 to the 12th power TeV over c squared. But we don't see any magnetic monopoles. So the question is, where the heck are they? Questions? Imagine you have questions about the strangeness.
For a particle, that's really big, isn't it?
It's chunky.
Yeah, I was about to say that's.
Right. In fact, I'm sitting here thinking, so a tera electron volt, I'm wondering if I meant to say just 1 TeV over c squared, because 10 to the 12, so it's huge. Well, yeah, but in any case, it's huge. I need to double check that, because I kind of don't believe myself. But I need to double check that. So the basic idea is, the inflationary hypothesis is there was a time in the early universe when there was a cosmological constant that was much bigger than it is now, due to some different quantum field that produced a negative pressure that therefore produced a sort of anti-gravity that caused the universe to accelerate much more than it is now. Such that when the universe was between about 10 to the minus 34th and 10 to the minus 32nd seconds old, so for a period of about 10 to the minus 32 seconds, the universe underwent a tremendously rapid expansion, such that something that was much smaller than a proton in 10 to the minus 32 seconds becomes like bigger than the solar system. So just this extremely rapid expansion of space. And it solves these problems by essentially saying, okay, even if the universe was strongly curved, strangely shaped early on, if you rapidly expand it, then it's like blowing up a balloon, right? If you went like this super balloon, if you had this tiny little balloon and you blew it up to a very large radius, each part of the surface looks very close to flat. So the idea is that maybe overall the universe is this really weird, strangely curved thing, but the part of the universe that we can see is such a tiny fraction of it that the part we're in looks flat for all intents and purposes. That's how it solves the flatness problem. As we'll see, it solves the horizon problem by saying that regions that look like they were never talking to one another, if you account for inflation, they actually were talking to one another before inflation, and then they stopped talking to one another after inflation and up to the time of recombination. But because they had been talking to one another before inflation, they were able to come into thermodynamic equilibrium. And it solves the monopole problem because you can show that even with this incredibly high density of monopoles in the early universe before inflation, after inflation, they would have been spread so far apart from one another that we wouldn't expect to see one monopole even anywhere in what we can currently observe of the universe. So in other words, the monopoles are still there, but they're spread so far apart now after inflation that we wouldn't expect to see one in our entire observable part of the universe. Yes?
Flatness of omega, is that equal to 1?
So, so in other words, if the universe is flat, omega would be exactly equal to 1. You can show, but when we say, why is the universe so close to flat, we mean even if omega was 2 right now, it would have had to have been unbelievably close to 1 earlier on. Because remember, at one point we showed that omega doesn't change sign. If the universe is flat, it's always flat. If it's positively curved, it's always positively curved. Same thing for negatively curved. We can also show that omega gets further away from 1 with time. And we're not going to have time to go through the math here, so I'll refer to the notes. But I'll quote some results, that if omega is anywhere close to 1 now, it had to be unbelievably close to 1 early on. And that's what begs explanation. In other words, for it to be anywhere close to 1 now, in early times, it would have had to be incredibly close to being equal to 1. And then it's kind of hard to understand why it would be so close to being exactly equal to 1, whereas inflation makes it not surprising, because inflation would run counter to this. In inflation, instead of omega becoming further from 1 with time, during inflation it would become closer to 1. So the idea is omega could have been very far from 1 right before inflation, but after inflation it would have been driven to being very close to 1. And then, after inflation stopped, it would be so close to 1 that it would not be surprising that it's still close to 1 today. It would have been incredibly close to 1 after inflation, such that it's not surprising that it's still close to 1 today, 13.30 years later. Okay, what other questions do you have? All right, so continuing. equation, we can show, see my notes for the details, that 1 minus omega is equal to a squared, scale factor squared, times 1 minus omega naught. Omega naught would be the present value of omega, divided by omega r naught, the current value of the radiation density parameter, plus a times omega m naught, the current value of the matter density parameter, plus a to the 4th times omega lambda naught, the current value of the density parameter associated with dark energy, which remember should just stay constant. So really I don't even, strictly speaking, need the naught subscript there. Plus a squared times 1 minus omega naught. And in the very early universe, when A is very small, these last two terms will be really tiny compared to the first two terms in the denominator, so we can ignore them. In the early radiation and matter-dominated universe, we can safely ignore the last two terms in the denominator. So remember, before we talked about there was a time when radiation and matter densities were equal to one another, and that's when the universe transitioned from being radiation-dominated to matter-dominated. So let's go back to that time and plug in the value of A for that time, and figure out that given what omega naught is now, what would omega naught have been back then? Any idea? Matter and radiation densities were equal. When the scale factor was given by epsilon radiation today over a to the 4th equals epsilon matter today over a cubed. Because remember, the matter density goes like 1 over a cubed, the radiation density goes like 1 over a to the 4th. So we can see when they were equal by solving for A, when those two quantities are equal. Because this is how radiation depends on A, this is how matter depends on A. Says A is equal to the current radiation density divided by the current matter density, which is the same as the ratio of their density parameters. And we already had looked before and said that Currently, the radiation density is 8.4, 10 times 10 to the minus 5. Currently, the matter density parameter, I should say, is 0.26. So you get 3.2 times 10 to the minus 4 for the value of the scale factor back then. The universe was about 72,000 years old back then, and it was that fraction of its present size. Plug that into that equation over there for 1 minus omega, we find that 1 minus omega then was 6.2 times 10 to the minus 4th power of what 1 minus omega is today. So in other words, whatever the deviation of omega from 1 is today, back then, it was only 6.2 10,000ths as big. It was much smaller back then than it is today. So if the universe is close to flat today, it was really close to flat back then. That's the basic idea with the flatness problem. The further back in time you go, if the universe is at all flat today in the standard scenario without inflation, then the universe would have had to been really, really close to flat at earlier times. If we go all the way back to the so-called Planck time, when we think all four forces were united as one, were united. Not that we have such a theory yet, but we can estimate how old the universe would have been by doing some dimensional arguments. Or last unified, so before this time they were unified. That's estimated to be when the universe was about 5 times 10 to the minus 44th power seconds after the Big Bang, if it even makes sense to talk about time at that point, because we don't have anything, we don't have a theory that allows us to really say anything before that. So does it mean anything to talk about time before that point? But anyway, assuming it does, that would be about an age of 5 times 10 to the minus 44 seconds for the universe, and a scale factor of about 2 times 10 to the minus 32nd power. We get that 1 minus omega is 4.8 times 10 to the minus 60th power times 1 minus omega naught. Oh my God, is what. So, so even if the scale even if omega was very different from 1 now, like 10 or 0.1 or anything like that, even 1,000 or 1/1000th, it would have to have been extremely close to 1 in the very early universe. That's the flatness problem, because we don't have a fundamental reason why the universe should have been born close to flat. That's the idea. Any questions? Okay. Which can, I realize, be like, I don't even know what to ask. So that's okay too if you just want to say, I don't even know what to ask. What?
I'm great.
You're okay. Okay. All right. Good. All right. So, let's talk about inflation. No, let's take a break. It's 3:05. Let's take a break. And we'll talk about inflation.
To Hogwarts.
To Hogwarts, yes.